Hello and welcome everybody to the Energy for Sustainable Development Group. We're very excited to have you with us and excited to share our ideas. Now, meeting the UN Sustainable Development Goals is no easy task, but we've got cases from all over the world because the development goals are really interconnected, driven by access to clean and affordable energy. Energy can enable healthcare, schooling, education, built environment, and food security, to name a few. We're also increasingly aware that it's the poorest of the poor who are at the most risk of the effects of climate change. And so the balance of having the right energy, being affordable and environmentally friendly, are all having to be taken into account. Now, as I said, we're a diverse group calling from all over the world, and we're going to be looking at cases at different levels of implementation. So we hope that this presentation has something for you that you can take away and learn from. We're excited to have you.
Thank you, Nick. Hello, everyone. My name is Michael. I'm calling in from London. And today I want to discuss with you all the opportunities for strategic clustering for the promotion of sustainable development in West Africa. But first, I want you all to try and imagine a world filled with darkness. You probably can't. However, the same cannot be said for the 940 million people spread globally who lack access to electricity, 64% of them residing in sub-Saharan Africa. Now, even though there has been significant progress in bridging the energy gap over the past few years, universal access to clean and affordable energy is far-fetched from being achieved by 2030, especially since Sub-Saharan Africa is set to propel the world population to 10 billion by 2050, which will instigate a tremendous rise in energy demand. This bubble graph shows a correlation between GDP per capita and energy consumption per capita in industrialized and developing countries. Now, developing countries like those in sub-Saharan Africa lack access to energy, proper infrastructure, resources, capital, and the necessary support to meet this rising demand, which has led to an increase in energy poverty across the region, plunging it into a pool of socioeconomic repercussions, impeding their quality of life, their economic productivity, and development. On the other hand, industrialized countries like the US, UK, France don't face these issues as a result of their universal access to electricity. Now, my methodology follows a three-pronged approach. First step is data collection of social, economic, environmental, political, and energy status quo of all 46 countries in sub-Saharan Africa. Second step is a comprehensive data analysis that utilizes socio-economic indicators such as GDP per capita, energy consumption per capita, unemployment rate, access to electricity, to allow for an easy and transparent comparison between the four different regions, because the task or the objective of the second step is to prioritize one region. Now, from the obtained results, West Africa was chosen, and that enabled me to proceed to the third and final phase of my project, which is to perform a SWOT analysis that identifies the strengths, weaknesses, opportunities, and threats of all 16 countries in West Africa. And based on different thematic analyses, I was able to cluster multiple countries together for individual and mutual benefit. Now, even though clustering countries through SWOT analysis is the main topic of my thesis, however, it is a long-term strategy that cannot be implemented currently or even in the next decade for that matter. So regional leaders need to prioritize on their short and medium-term plans, which is to improve energy access through the installation of off-grid renewable energy system, which yields multiple benefits, as well as expand and enhance the main utility grid, which are two areas that Rachel will be discussing afterwards. However, a common threat that hinders the region's progress is primarily due to bad governance and corruption that needs to be corrected. Now, for the region's long-term strategy, a SWOT analysis is performed based on the following different themes. So we have energy, GDP, hydrocarbon, and natural resources. From there, I was able to cluster multiple countries together into 4 different groups, where these clusters can utilize their combined strength and complement each other's weaknesses. Now, a vision for the region is the formation of a synergy where these multiple cluster groups can start to collaborate and cooperate with one another to form one giant network of resource, energy, knowledge, and technology trading, which will eventually lead to a reduction of energy poverty, promote sustainable development, and boost economic growth, mainly through interconnection regional trading of the resources and electricity. This will provide job opportunities, improve health, safety, education, as well as mitigate the effect of climate change, aiming towards a greener environment and a greener future. And now Rachel will be discussing the different electrification strategies based on a country level.
So thank you, Michael. As you mentioned, electricity access is still an important issue in developing countries. I, Rachel, currently in London, will be looking at electrification strategies at a country level. The general strategy of South Asia developing countries for rural electrification is grid expansion. However, given that most of rural villages are located far away from the city center, expanding the national power grid to those areas can be very costly and can result in bad quality electricity. Indeed, people can experience blackouts or have not enough electricity to use all their appliances at the same time. Developing countries, such as Sri Lanka, where the electrification rate is 98%, make it seem like there is no further work to do in terms of electrification, although villages still suffer from bad or inexistent electrification. Therefore, my research will focus on a district of Sri Lanka named Batticaloa. As Michael mentioned as well, two methods can be used for rural electrification. One is grid expansion, the most used technique in South Asia, and the other one is the implementation of mini-grids. So mini-grids use a combination of solar PV, batteries, diesel generators to supply enough electricity to meet one or several village electricity demands. And although both methods are often looked at in isolation, it can be beneficial to combine them to electrify remaining unelectrified areas in a region. So the goal of my research is to compare and combine mini-grids and grid expansion electrification methods to reach 100% electrification rate in a region of Batticaloa at the lowest cost possible. So the region chosen as a case study is Mainmunai West, which is one of the poorest regions in the district of Batticaloa. So to combine and compare mini-grids and grid expansion, the first step has been to design an optimized mini-grid that met the electricity needs of an average unelectrified village. So the mini-grid design uses solar PV and battery energy storage, and it is upgraded every 5 years to meet an increasing electricity demand. Then, once the mini-grid was designed and all of its characteristics were known, a model was built to decide what would be the cheapest electrification methods for each village or the region, knowing their coordinates. So 3 electrification methods were considered, the first one being using a mini-grid, the second one to import electricity from another village that has a larger mini-grid, and the third one to import electricity from the national power grid by using distribution network. And indeed, although the price of the electricity produced by the mini-grids is higher than the electricity price of Sri Lanka, over long distances, high costs are associated with distribution network expansion and can result in electricity being more expensive than mini-grid electricity. So the results suggested by the model are illustrated on the left. So the areas in color are supplied by mini-grids, which represent 80% of the electricity generated, and the rest in white is supplied by grid electricity. Besides, as you can see, villages 1 and 3 share mini-grid produced electricity to benefit from economies of scale. And on the right side, the general Sri Lanka strategy is illustrated. So all villages import electricity from the grid substation using distribution line illustrated in blue and brown. So a comparison of the two options reveals that the cost-optimized solution of the model is almost 3 times less expensive and 2 times cleaner than the grid expansion option. So the key takeaway here is that this case study on Mainmunai West shows that using mini-grids for rural electrification can be more cost-effective than grid expansion only. Besides, considering electrification at a regional level instead of a community level is beneficial. However, other factors such as the availability of skilled workers, business model, payment methods, etc., can have an impact on the choice between mini-grids and grid expansion, and they have not been taken into account by the model. Therefore, the practical implementation of those electrification strategies will be discussed by Nick right now.
Thank you, Rachel. My name is Nicholas Rohani. I'm calling in from Johannesburg, South Africa. Now, as has been mentioned by my 2 previous colleagues, electrification is a huge challenge, And as Michael mentioned, sub-Saharan Africa is increasingly becoming the concentrated home of the unconnected masses, who are mostly rural populations. Now, along with this, sub-Saharan African governments have limited public funding. Their balance sheets are becoming increasingly debt-laden. However, as Rachel mentioned, mini-grid and off-grid technologies are coming to the fore, and innovative private funding solutions are becoming more and more mature to be able to tackle this challenge. However, these solutions bring their own sets of challenges, mostly institutional, based around the governance. How do we actually govern decentralized technological transformations? Well, that's the question that I look forward to answering. My approach was to try and design a system using socio-technical analysis to be able to examine how these energy transitions can take place in sub-Saharan Africa. I iteratively refined this system using literature reviews and expert interviews, and in the end landed on a solution which combines the power of web platforms for scaling and network effects, as well as empowerment programs which unlock the capacities of local populations, and then leveraging knowledge sharing and information systems across the diverse sets of environments that exist in Africa, since lessons that could take months to learn in one place might take years to learn in another. And so by developing the information infrastructure, we'll be accelerating the process, Sustainable Development Goal 7. This entire approach ended up with GroundSpark. Now, GroundSpark is a system which empowers and enables end users to be active participants of their own energy transformation processes. It does it by combining two separate subsystems. First of all, GroundSpark Training, which is a decentralized capacity building system, which enables people on the ground within these local communities to gain basic technical acumen to be able to articulate their needs better to energy service providers. And then with this increased capacity, we give them access to the GroundSpark web platform, which amplifies that capacity by facilitating networks between local communities, funders, and energy service providers to accelerate these energy transitions and enable end users to have a better say. But also there are advantages for energy service providers who have shorter routes to market, market mapping tools, and are able to find the right funding partners for their projects. Also, by enabling end users to have a greater say, risk is shared across the network, and funders have lower problems with getting local communities to actually engage. Now, looking ahead, it was important to actually think about the rollout of the GroundSpark system. We're going to take a gradual and iterative approach. GroundSpark is going to start in urban areas, replacing fossil fuel generators, since urban areas don't have as many operational failure points as rural areas might have, such as connection to data and actually accessing those places physically. But then slowly, GroundSpark, as it gains capacity, will move into rural areas strategically using energy service provider partners who are already operating in those areas. But beyond just catching up sub-Saharan Africa in electrification, the GroundSpark model is generalizable in that it enables local communities to have a greater say in shaping their socio-technical environment, a pattern which the whole world can follow as even industrialized nations deal with the destabilizing effects of social media. This model, therefore, is generalizable and applicable to other developing contexts as well as other innovative technologies, such as the one that Hua Chu is going to show you now.
Thank you, Nicholas. Actually, besides West Africa and Sri Lanka, Mongolia is a developing country, also facing the energy challenge. Hello, my name is Hua Chu. I come from China. My piece is to conduct a life cycle assessment of ammonia utilization as a green energy vector in Mongolia. The main objective of my project was to understand the role of ammonia as a green energy vector, explore the potential technology that can provide reliable, stable, and sufficient energy using ammonia as a fuel, and also examine the feasibility of ammonia as a potential fuel in Mongolia via LCA study. Mongolia now is facing three main challenges. Firstly, the energy demand is increasing. Mongolia thereby needs to secure more reliable energy, which will ensure its long-term energy supply. Secondly, Mongolia's power and heat supply is dominated by coal-fired plants. These power plants cause serious environmental pollution. Certainly, its GDP highly relies on export commodities, especially in coal. With the current tight economic climate, the government of Mongolia recognized the significance of green growth in its long-term economic strategy. Therefore, ammonia is a good choice to solve those challenges. The combination of ammonia production from coal and the various ammonia end-use technologies will play an important role in a potential ammonia economy, where the produced ammonia as a green energy carrier can be utilized domestically or as an exported commodity. A LCA of ammonia from storage, distribution, and utilization with NOx reduction was conducted to evaluate the feasibility of using ammonia as fuel. According to my LCA result, the storage and distribution process has negligible impact on the environment, as they can emit little greenhouse gas during the operation. In the utilization process, there are various alternatives that must be evaluated to choose the most suitable technology. From the environment point of view, the pure ammonia combustion in gas turbine is the best choice, since it has relatively little harmful substance to environment. However, considering about that, the ammonia and the natural gas mixture fuel to combustion in gas turbine is the suitable choice, since the modeling result shows that it could generate helix electricity under the same amount of ammonia as the input. The only pollutant gas from burning ammonia is NOx. Therefore, NOx reduction is the necessary process to release environmental burden. The world is experiencing a profound energy transition, shifting from an energy system based on fossil fuel to one based on renewable energy. From LCA results, ammonia might be an excellent transition fuel. It can be burned directly in power engines with no carbon emissions, and it is easier for storage and distribution. However, the wide use of ammonia as a combustible fuel is challenging due to its toxicity, high cost of production, and high requirement for power engines. For example, one of the big disincentives to use pure ammonia combustion in gas turbine has been the technical difficulty and the cost of such an enterprise. The gas turbine is to be upgraded to two-stage combustion chamber and requires very high pressure as well. The relevant technologies for using ammonia is still at the research level and far from commercial implementation. But Taiho will introduce a quicker and cheaper way for energy transition from coal if you are in a rush.
Thank you, Huachu. Yeah, as mentioned, my thesis focused on coal to biomass conversion as a possible pathway to lower carbon future. My name is Teo, and I'm calling in from London. My thesis more specifically focused on techno-economic analysis of coal to biomass conversion in Slovenia on a case study of an important coal power plant, Šoštanj. But let me first give you the brief introduction to the challenge Slovenia is facing in the near future. Slovenia is a member state of European Union, and EU tries to be carbon neutral by 2050. And in order to achieve that, it sets milestones, one of which is in 2030, where 40% greenhouse gas reduction is required. And every single member state shares its own task in reaching this goal. Slovenia, for example, has to supply 27% of final energy from renewables by 2030. And in order to achieve that, Slovenian government is planning to implement 43% renewable electricity by 2030, whereas at the moment, only 32% is supplied renewably. Slovenian electricity sector is dominated by a single nuclear power plant, Krško, by thermal generation, of which is aforementioned thermal power plant, Šoštanj, with the rest being hydro, solar, wind, and already a high import dependency is evident. But further to that, in 2043, nuclear power plant will have to be decommissioned, and coal generation will probably have to be decommissioned prematurely as well as a result of environmental pressure and this can lead to significant import dependency. My thesis focused on 3 core research goals. One of them was to obtain a levelized cost of electricity of biomass conversion specifically for Slovenia. The second one was to obtain the share of renewable electricity in Slovenia and whether this could reach the goals if conversion does take place. And the third one being the sustainability of biomass if that is supplied domestically. The results show that an LCU of just under 100 euros per megawatt hour can be obtained if biomass is supplied from Slovenia, whereas just above 120 euros per megawatt hour is seen if biomass is supplied from Norway. In comparison to existing business as usual with coal generation, we can see that biomass is still more expensive and therefore requires government subsidies. Interesting is also a comparison to nuclear and solar currently proposed by Slovenian government. And we can see that, yeah, both nuclear and solar can be cheaper than biomass. However, they come with their own issues. And perhaps a better comparison of biomass is with solar coupled with battery storage. And in that case, biomass does prove cheaper. The share of renewable electricity in 2030 shows that more than 51% of electricity can be supplied renewably if thermal power plant Sjostan undergoes conversion. And that is enough to reach 43% goal. But in terms of sustainability, the study actually showed that there is not enough biomass available in Slovenia to sustainably supply power plant Sjostan. And as a result, resource depletion would occur and the forest coverage area could shrink from existing 58.1% down to as little as 49.3% in worst case scenario. And that would lead to carbon emissions, net carbon emissions. However, those would still be half that of emissions with coal generation. So key takeaways can be taken from my thesis. One of them is that, yes, biomass conversion can be an effective strategy for Slovenia specifically to meet short-term renewable goals and quick transition from coal. However, caution is needed because resource depletion can occur and as a result, net carbon emissions. So further into the future, additional solutions will be needed, such as better energy storage or frequency control in order to allow higher implementation of other renewables. And Chuyang will tell you more about advanced frequency control.
Okay, thank you, Theo. My name is Chuyang and I'm calling from China. I will be talking about issues with future power system with increasing penetration of renewables. In the UK, electricity generation from renewables is important in order to achieve UK's climate commitment of net zero carbon emissions by 2050. Also considering the increasing demand for electricity as electrification of heat and transport continues, the uptake of renewables in electricity generation will become even more crucial in facilitating the transition towards a low-carbon economy. Among those renewables, onshore and offshore wind in the UK are the key power sources. Due to the limitations of viable onshore sites and the abundant offshore wind resources, the offshore market has been expanding rapidly and reaching maturity during recent years. The current capacity in operation is 8.8 gigawatts, and is set to rise to 40 gigawatts by 2030. However, this increasing share of wind energy will pose a huge challenge to the technical and operational aspects of the UK's electrical power system network. Unlike conventional gas and coal power generators, power electronics converters are used in wind farms to connect to the grid. For offshore wind farms that are far from shore, voltage source converter-based high-voltage direct current links are most commonly used. Due to these different characterizations, the structure of the power system has been significantly changed. This is demonstrated by the August 2019 blackout in the UK, which raised alarms about the system inertia level and frequency response. The insufficient system inertia has resulted in a rapid change of frequency, with the frequency deviation exceeding the value of the power system protection scheme, leading to wide-scale power outage. It is therefore important to learn lessons from the blackout, and especially in the future power system, where wind power will dominate the generations. With additional control loops, a variable speed wind turbine can monitor its active power output within a short period and hence provide a response. In my research, the power system performance of wind providing response with conventional control system has been analyzed and then compared with a proposed fuzzy logic control system. Conventional control systems use fixed controller gains, whereas fuzzy logic controllers could vary the controller gains according to different frequency change and rate of change of frequency, and therefore perform dynamically during different stages of frequency response. The active power provided is done by operating the wind turbine generators under deloading mode instead of maximum power point tracking, leaving a margin for providing response. By this way, the frequency drop could be slowed down, and the maximum frequency deviation could be reduced, and the frequency restoration could be accelerated. The results show that having wind providing response with conventional controllers could improve the frequency response, and with fuzzy logic controllers, this could be further improved. As a result, in the context of decarbonization of power system with reduced system inertia, it is important to improve the frequency response to ensure the safe and stable operation. The evaluation of potential consequences and of wind farms connecting to the future power system, and the necessity of wind turbine generators in providing inertia contributing to power system frequency stability require further discussion, especially concerning how to utilize this inertia to improve power system stability and how to control this inertia to enhance the dynamic performance of the power system. The effectiveness of these approaches will be key to determine the value of different wind turbine generator control methods and may further decide whether it is applicable to other renewable power sources. Thank you.
Thank you, Shuyang. And so, as you guys have seen, we've really introduced ideas at many different levels of technical governance, strategic implementation of ideas for energy transitions and energy access. But as we said at the start, the Sustainable Development Goals are highly interconnected, and it's more than just energy. Our next two presentations from Jasmine and Hasib are going to be tackling food and the built environment.
Thank you, Nick. Hi, I'm Yasmin, and I'm calling in from London, and I'll be talking about the intersection of the agriculture and the energy sector. In fact, food security is important to all of us. The COVID-19 pandemic has shown that this is not only a problem of developing countries, but that actually even in industrialized countries, such as the UK, the food supply chains are very fragile and we cannot cope with short-term disruptions. In addition to that, the agriculture sector is the second largest greenhouse gas emitting sector after the energy sector. This clearly shows that we need to transition towards a more sustainable food system. A potential complementary solutions to future food systems is urban agriculture. Previous studies have shown that it can provide a range of social, environmental, and economic benefits. By producing food more locally within the city, you reduce transport emissions and also can benefit from urban symbiosis potential, such as using waste streams for the growing medium for fertilizer or even using waste heat in the farm. One system is controlled environment agriculture, which maximizes the yields and also the resource efficiency. However, its environmental performance is still very much debated and hasn't been studied yet a lot. In fact, it's not clear yet what the main drivers of environmental performance of these systems are, and it's therefore not clear how we can optimize it. I therefore, in my thesis, tried to tackle this research gap by conducting first a Monte Carlo simulation, where I sampled 24 input parameters that are related to farm design, operation, urban symbiosis potential. Afterwards, I quantified the energy and the water demand, as well as the crop yields of these different samples. These were then used as inputs for a life cycle assessment, where the environmental impacts were quantified. And afterwards, a correlation analysis was run between the input parameters and the environmental impact scores in order to identify and quantify the main environmental impacts. The findings of the study show that cooling demand is the most influential parameter on climate change as well as water depletion. Since cooling demand is mainly driven by the climate is also one of the most influential parameters, and it ranks number 2 for climate change. Moreover, the electricity supply system, the cooling supply system, the growing temperature, and the growing medium are among the 5 most influential parameters of climate change of controlled environmental farms. On the right-hand side, you can see that cooling demand accounts for nearly 60% on average of all climate change impacts, whereas building symbiosis or distribution parameters such as transport and packaging are actually not of high influence. Moreover, the study also showed that different types of farms are suited for different climates. So in hot climates, the study showed that plant factories are more suited, since plant factories have higher insulation, which therefore would reduce cooling demand in hot climates. Whereas in cold climates, greenhouses are more appropriate because cooling demand is reduced in these climates, and therefore greenhouses would benefit from solar radiation, which would reduce artificial lighting requirements. What does this mean? This means that locally grown produce is not necessarily more sustainable. Actually, to really optimize the environmental performance, have the lowest impact, we really need to reduce cooling demand. We should focus therefore on the space conditioning, on the growing medium, and also shifting towards renewables and absorption chillers for cooling technologies. Moreover, location of the farm should be based on the climate, the farm type, the synergies in order to reduce the cooling impact of the cooling technology, and also on the availability of space, as larger farms actually reduce the environmental performance, the environmental impact per vegetable. Finally, the farm design should be adapted to the climate. However, if we really want to transition towards sustainable cities and communities, we also need to take into account the infrastructure and the materials that we use. New alternatives were investigated by my colleague Hasib and will now be further explained.
Thank you, Yasmin. My name is Hasib and I'm calling from London, and I will be discussing Hempcrete, which is a green building material, and its potential ability to decarbonize the built environment. People are surrounded and live in the built environment, but often forget its impacts on society. The building industry is accountable for some of the largest direct and indirect greenhouse gas emissions in the world. This is often attributed to the industry's high utilization of raw materials. And with a projected $53 trillion to be spent on construction globally between 2010 and 2030, concrete, the most abundantly used building material in the world, is expected to be used immensely. Concrete has three major problems, which are the embodied emissions, the overutilization, and the industry's outlook. The embodied emissions of concrete is a huge point of concern, as it is a very carbon-intensive substance due to its utilization of cement. Cement production accounts for up to 7% of the world's anthropogenic CO2 emissions and is listed as the fourth highest source of emissions in the world. Taking a look at the industry, they have done an amazing job of decarbonizing since the 1990s. They've dropped emissions by 17% by integrating elements like renewable fuels. However, this has been overshadowed by an increase in concrete usage of 72% over the same time frame. The net effect has caused an increase in emissions by 44%. Although the industry has been proactive in the past, their outlook is not promising. Only 22% of the industry leaders are expected to adhere to the Paris Agreement. One of the promoted solutions in the building construction industry is the utilization of products that are more sustainable. These products have positive impacts on the life cycle and operating emissions in the built environment and are being passively driven by policy and heavily pushed by client demand. With an increase in demand for sustainable projects, it is expected that the construction material industry must accommodate by developing cleaner alternatives to concrete. Linking these sectors together is crucial in progressing forward with a cleaner future. One of the green building materials that is gaining much traction is Hempcrete, which is generally a combination of hemp fiber, water, and lime binder. As a series of benefits, but chief amongst all of them is Hempcrete's carbon negative embodied emissions due to its utilization of plant material. From a materialistic standpoint, this makes it a suitable alternative to non-load bearing concretes. In this study, two different models were created to assess Hempcrete's embodied emissions and its ability to satisfy the concerned stakeholders. A life cycle assessment was constructed to calculate the embodied emissions associated with the production of 1 metric ton of Hempcrete in the US. Meanwhile, a systems dynamics model driven by profitability was made to explore the temporal effects of introducing a new product into the market by looking at a 10-year projection. The LCA showed showed that a metric ton of hempcrete emitted around -44 kilograms of CO2, which made it 158% less carbon intensive than non-load-bearing concrete. Meanwhile, the systems dynamics model showed in the most optimistic scenario, hempcrete took up a 1.5% market share, which accounted for around 1.3 million tons of hempcrete in the infrastructure. The introduction of hempcrete was able to displace around 180 megatons of CO2 in a 10-year timeframe. Based on the results found in the analysis over green building policies, hempcrete was proven to be a suitable replacement to non-load-bearing concrete. It was profitable, it fulfilled the materialistic qualities, and it was significantly less carbon intensive. It also satisfied all the stakeholders' needs and adhered to government policies in the US. Hempcrete's introduction into the industry seems very promising and should be further explored to help reduce the carbon footprint of the built environment. Thank you for listening, and now Nick will conclude by sharing general trends amongst all the studies analyzed.
So there you have it. We've presented to you a diverse set of thesis ideas from a diverse set of locations around the world, but we did notice that we all had some common findings. First of all, the power of unity. By bringing diverse entities together, we unlock potential within all of them and enable more efficient outcomes, whether that be different governments in sub-Saharan Africa or new technologies for rural electrification. Then also the value of strategic approaches. By really systematically analyzing these systems, we're able to identify synergies and trade-offs that ensure that no one gets left behind in the decision-making process. Finally, the value and need for facilitation in these energy and development transitions is super important to ensure that the right qualities of different actors are leveraged in interactions to ensure that the system is successful. Thank you so much for joining us. We hope that you've learned something and enjoyed the presentation. We hope that slowly and surely these ideas will help the development world move forward and in the end make the world a better place. Thank you.